Hello ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be talking about an introduction to kinetics and how to speed up chemical reactions, so make sure that you follow along with your notes. Then if you have any questions, you ask me tomorrow. Okay, so kinetics. Something that we haven't actually talked about at all is how do you speed up chemical reactions. So here's the thing. We've talked about different types of reactions, we've talked about many of the different aspects of what make a chemical reaction function, but never really the actual speed of a reaction. How fast do reactions happen? So kinetics is the study of what we call reaction rates. A reaction rate is the change in concentration of a reactant or product over time. So you can really think of that as just how quickly or how slowly a reaction occurs. So if we had a molecular, speed gun, how quick do different reactions occur? In order to understand how fast chemical reactions happen, we have to understand what we call the collision model. In order for any chemical reaction to happen, the reactants have to collide with each other in the proper orientation and with enough energy. Now, when we use the term orientation, we basically mean facing the right direction. Now, I know that seems like a strange concept, but you can picture just sort of a molecule that looks maybe something like this, like a water molecule almost, that is going to be colliding with something that's like, I don't know, like this. And so let's say that, your product for this reaction ends up looking like this. This is your product. So if this molecule, and let me use my pointer, if this molecule here collides with this molecule facing this direction, it's probably not going to make a chemical reaction occur. Why? Because this is facing the wrong way. A better orientation for this would be if this were flipped. Because if it was flipped like this, then definitely these two things right here, when they collide, we'll end up with something that looks like this as a product. So it really is just, are they facing the right direction, and do they have enough energy? Now, what happens if a chemical reaction doesn't have either proper orientation or energy? We call that an ineffective collision. In other words, they just bounce off of each other. So, I mean, I'm pretty horrible at drawing things, but what that means is if you have a reaction where two things do not really, react in the proper way because either they're not facing the right direction or they don't have enough energy, they will literally just collide like this, and then this one will just bounce that way, and this one will go that way. They'll just go opposite directions, and so it's called an ineffective collision because literally nothing actually happens. So obviously there has to be a converse to this. What's the opposite of an ineffective collision? Well, if the orientation and the energy are correct, we call that an effective collision. And this is a really good example. So we have NO plus O3, and then you have, as a product, NO2 and O2. So notice, in order for this reaction to happen, first of all, you have to have the right amount of energy. You can't really see that in this picture, but you can definitely see the orientation. So look and see. Look over here at NO, and then look at O3. Notice that the NO, the N, is going to barely hit the edge of the O3 molecule. And when it does that, these two things right here stick to each other, and you end up with your product over here. Okay? That's an effective collision. Now picture if this and this were sort of flipped around a little bit. If they were flipped around, would you get the same interaction here and end up with an effective collision? It really depends. If the NO here were now flipped the opposite direction, you'd have oxygen touching more oxygen, and so nothing would actually happen. So I know this seems like a little complicated, but it really is just a model of what does it take for a collision to occur, and how do we get chemical reactions to really happen. So what are some ways to speed up chemical reactions? So there are a couple of things that we can do. We could increase the concentration, meaning the amount of the stuff itself. Okay, so if we increase the concentration, obviously that's going to mean things are going to speed up because we have more stuff. Okay, so if you increase the concentration of your reactants, that kind of just makes sense. What else can we increase? What if we grind it apart into pieces, and so we increase the surface area? Okay, if you grind something into pieces, that means you increase the surface area. Things will speed up. What if I change the temperature? So if I change the temperature, that could definitely have an effect, especially since most people think if you heat something up, it'll speed it up. And that is true for the most part, but you never know. So change the temperature. What if I increase the pressure? Increase pressure. Then I'm pushing things together. Maybe that'll speed up my reaction. And then what if I add something? What if I add a catalyst? Why can't I spell catalyst? Or maybe an enzyme. If I add an enzyme or a catalyst, it will speed up chemical reactions. Let's go through these one at a time. So increasing concentration, that's the first one. So the more reactants I have, the more effective collisions will be likely to occur. And that is just a simple process of probability. If I only have 2 molecules, let's say, inside of a box, that's it, just 2 molecules, what are the odds of them making a product if, when I combine them together, I make one product? It depends, and it depends on a lot of things. They're going to be bouncing around in a big container. I have 1 molecule, let's say, here, and I have 1 molecule here. They could bounce around for a they could bounce around for a really long period of time and never really hit each other. You know, this could go here and there and then all over the place, and they may never collide. But if instead of just having, sort of 2 molecules, what if instead I have a whole container filled with these molecules? Then I'm much more likely to have a collision occur. And I always said, pretend you have bumper cars. The more cars you have in the space, the more likely you are to collide. It's kind of like if you were at a carnival and you had bumper cars and you were the only one driving one. It would be kind of boring. But the second you add way more cars, you get way more collisions, and that is way more fun. That's the way it works in chemical reactions. The more cars or reactants you have, the more likely you are to collide. Increasing surface area. Surface area is the total area of the faces on the surface of an object. Okay? Smaller objects, by definition, have a larger surface area, and it kind of makes sense. If I have a gigantic cube of a substance, and I compare that to tiny little cubes of a substance, okay? These tiny little cubes that make up this larger cube, there are many more faces for me to get around and to use. So, I only have, a limited number of faces when I look at a cube, but each one of these little tiny cubes has all of these little tiny faces on them that I now have that I didn't have before. So when you grind something into pieces, you have increased its surface area. Okay? And so by increasing the surface area, the reaction is much more likely to happen. It leaves more area for the reactants to collide, and that's important. So right here we have, coffee beans versus ground up coffee. That's the reason why we don't just make coffee with, just whole beans, because it would take a really long time for all that coffee flavor to get extracted out of it. But instead, if you grind it into little tiny pieces, you have many more opportunities for those faces to come into contact with water, and so it becomes a much more potent flavor much more quickly. Here's just a more visual mathematical way of looking at surface area in case that seemed a little bit confusing. So let's say I have a cube like this, like number 1 up here, and it has a combined surface area of about 54 square inches. Now let's say I dissect this cube into pieces, so I start to dissect it. By simply cutting it in half and then cutting it again, I end up with a surface area of 108 square inches. Okay? And then if I divide that cube again into even smaller pieces, I get 162 square inches. So every time I divide something into smaller pieces, I actually get a crazy increase in surface area. What if I now increase the temperature or something like that? So if I change the temperature, I could change the amount of kinetic energy the reactants have. And so the higher the temperature, the more kinetic energy there is, and that could lead to quicker reactions. Reactants need to have the proper amount of kinetic energy in order for an effective collision to happen. So if I increase the amount of kinetic energy a system has, I'm probably going to be much more likely to have an effective collision. And we know this intuitively because it's easier to dissolve dirt and grease in hot water as opposed to cold water. Why is that? That's because in hot water, the molecules of water are hitting the dirt and grease molecules with enough kinetic energy to dislodge them. Okay, and so another kind of application of that would be if you've ever tried to dissolve sugar in hot coffee versus in iced coffee or cooler coffee. It's always easier in hot liquid to dissolve something than it is in cold liquid, and that's just because of the amount of kinetic energy that the water molecules possess. Pressure. So what happens if I increase the pressure? The higher the pressure, the more collisions occur. Why? Let's look at these two situations. So this situation is under low pressure. This situation's under high pressure. Which one is going to have more collisions? Well, obviously the one with high pressure is going to have more collisions because they're being forced together. So there's a much more likely chance, at least, that it's actually going to collide with the proper amount of energy and in the right orientation. Why? We are forcing reactants together. Now this last one you've probably heard of in the past, but we're going to talk about it from a chemical perspective here. So catalysts or enzymes. What are catalysts? Catalysts are a broad category of substance that speed up chemical reactions, and they do that by ensuring molecules collide with each other in the right orientation. So orientation is taken care of by the catalyst. This also means, though, that they lower the amount of energy actually needed for the reaction to happen. So it kind of takes care of the energy component as well. Now, why lower the energy? Because if it takes less energy for a reaction to occur, now the reaction is much more likely to occur. So how do we write catalysts in chemical equations? Well, we always write them over the arrow in the chemical reaction. This is a real reaction that happens in cars, and so let me make sure I get this right. So it's 2 nitrogen monoxide and 2 carbon monoxide, okay, and that yields nitrogen and carbon dioxide. Okay, I need to balance that with the 2 here. Okay, so here's the thing about this reaction. This happens in a catalytic converter in your car, okay, and so it helps convert 2 pretty toxic reactants, nitrogen monoxide and carbon monoxide, into harmless, or at least more harmless, nitrogen gas, which is in the air we breathe anyway, and then CO2, which we also expel. So what actually helps in this process is a catalyst, and that would be platinum, so PT. And so if I write that over the arrow, that represents that it is a catalyst in this reaction. And so that really means, like it says for number 4, that platinum helps lower the energy for turning reactants into products, and as a result, it speeds up the chemical reaction. So this process would really not occur unless we had a catalyst there to assist in that process. One of the most common graphs of all time is this graph, okay? And so for some reason, they always love showing graphs like this on standardized tests. And so what we have here is energy graphed over time, and this is our reaction that occurs without a catalyst. So that's why it says uncatalyzed reaction. Whereas if now I'm using a catalyst, it lowers the amount of energy you need. And so since it lowers the amount of energy you need, it helps to speed up your chemical reaction. So the reaction with the catalyst looks something more like this. So if this line represents the amount of energy it takes that much less. So this difference between these two things. And that is enough to help speed up a chemical reaction drastically. So make sure you copy down. Actually, I'm probably going to show you another slide like this with it blank, because my drawing over the top of this makes it almost impossible to see. But this is the general idea behind why adding a catalyst to a reaction actually does speed it up. It lowers the amount of energy needed for the reaction to occur. Here's that picture again if you need to pause it. Alright, so what about enzymes? Enzymes are just proteins in living things that act like catalysts. So they're biological catalysts. What do? They help decompose or synthesize molecules by physically breaking or bringing them together. So if you've ever played a game like this before called Perfection, it's kind of like that, and we'll actually be playing it in class. Here's the other thing, though. In general, enzymes work based off of this principle. So you have your reactants, or substrate. You have your enzyme, which has a very particular shape, and then you have the active site, which is the place where this will attach. When that happens, it lowers the amount of energy. It also makes sure that everything is in the proper orientation, and then you end up with your products as a result. So the last important thing to recognize is that if you see something that ends in ACE, biologically at least, it's an enzyme. And so the last sort of bit here is about, how you can represent enzymes and chemical reactions. And so it's exactly the same as a catalyst, because an enzyme is just a biological catalyst, so you still write it over the arrow. So here's a real example. So we have C6H12O6, draw my arrow, and I'm going to be making alcohol, so that's C2H5OH and CO2. So that's definitely not balanced. Put a 2 here, and a 2 there, and now it should be. So what does this process? What helps to turn sugar into alcohol and then into CO2? It's a very particular enzyme called zymase. And so you would write that above the arrow. So in this equation, zymase helps lower the energy for turning reactants into products, and as a result, it helps speed up the chemical reaction. So that's literally it for ways to speed up chemical reactions. And if you have any particular questions, make sure you ask tomorrow.